vero? We are very late. We need to get on with it, as Monty Python would say. Okay, so it's your time to do your thing. I have one last thing to say. I have one last thing to say. We did these slides like 4 minutes before we started doing the presentation, so we did not have time to rehearse. And therefore, this will be very messy.
That said, we can start. What? Okay. I have sun in my face. That's very annoying. Okay, so bare metal lambda calculus. Now, show short film. We've done that. This is us at the start of this journey. And okay, lambda calculus. What do we mean with lambda calculus? Well, lambda calculus, a bare metal didactic argot compiled to assembly language, computes using lambdas, uta Stansburiana. And that, as you can imagine, is the name of our language. Now, the goal, well, was to compile lambda calculus into 16-bit assembly code so that we can write a bootloader. Imagining we are in a alternate reality in the 90s where imperative languages lost the war and pure functional languages, as they should have, won. So, okay, write a bootloader and somewhat useful programs. So, well, the idea is that why are we using 16-bit assembly? Because this way we can use BIOS interrupts and we don't have to do all the scaffolding to make stuff work. The ultimate goal, yeah, is to write a Lambda operating system. Now, some things like that exist, but ours is cooler. And yeah, ultimately, with our operating system, take over the world and assert Lambda dominance. First of all, what is Lambda calculus? I think you all know it, but let's recap it. Well, we have expressions that can be generated with this grammar. So we have name abstraction, application of a function, and variables. Intuitively, the name abstraction is like a way to write a an anonymous function. So these two things are equivalent. But of course, we can write this in lambda calculus. This is just standard notation, mathematical notation. Note that in lambda calculus, we don't have numbers, booleans, and all the other useful constructs that we have in regular languages. But we can encode them. We won't do that for reasons we will explain later, but you can encode them in pure lambda calculus. Now, with lambda calculus, we have an issue. We have an issue of names. As in lambda calculus, you can have two terms that are denotationally the same, but written in different ways because they use different names, it's alpha equivalents and so on. Now, there are ways to generate terms of lambda calculus automatically, nominal sets, but another easier way to do that and easier to implement is to use the De Bruijn indexes. So instead of using names for variables, we use some indices, which basically are used to determine how far in the syntax tree the variable has been bound by a lambda expression. So we have, I don't know if you can see them, but we have some examples. What if I don't know. Okay. We have examples of terms written in standard lambda calculus. For example, this is just a function that computes a sum. So lambda x, lambda y, x plus y. And the equivalent way of writing it in with De Bruijn indices is come on. Don't worry, I'll just say it. The equivalent way to write it with De Bruijn indices is lambda lambda L1 plus L0. Now we use L to denote that this is a variable, this is an index. Now that we have recapped lambda calculus, let's recap for who is not familiar with it. Assembly, okay? Basically, assembly is just the language of the operations that the native operation, the basic operations that a processor can execute. So it's just, that's why we call it bare metal, basically. So we have really low level instructions. And so the idea of putting a high level language like lambda calculus with a low level imperative language as assembly, as this assembly it's a mess. It's a mess. Trust me, you will see it later. It's a complete mess. Now, we've said that we want to use 16-bit assembly because this way we can use the BIOS. What is the BIOS? Basic input-output system. Basically, we have a set of basic functions, more complex functions than those of pure assembly. A set of basic functions to interface with the input and output systems of our computers. For example, to print a screen, read from keyboard, and so on and so on. And we will see that these basically are our effects in our language, we can see. Now, okay, we can, as we said, we can encode numbers, like church numerals and so on, conditionals, tuples, effects. No, effects. You can encode these things in pure lambda calculus, but we decided to implement them like more, not purely in lambda calculus, but by extending the language. This makes everything easier. Easier. not the easiest thing, but easier. So we extended the language with natural numbers, conditionals, so if, then else, tuples, and effects. Effects are basically the bias calls. So, okay, yeah, for natural numbers, of course, since we need to interface with low-level components, we support decimal, because why not? And we also support hexadecimal, because it's really way more convenient to handle bytes, like low-level bytes with hexadecimal. Otherwise, you have to keep a calculator when you're writing code. No. Okay, yeah, we also support characters to print. And okay, yeah, we do. The difference between signed and unsigned numbers at low level is a bit so, but we fully support unsigned numbers. Okay. Okay, yeah, as we said, we implemented the if then else and some classical comparison operators. Now, as you might know, tuples are naturally isomorphic to functions from a number, which is the number of elements in the tuple, to the domain of data. So in our language, instead of having tuples, like just a number of elements, you encode them using functions that take a parameter and return the corresponding element of the tuple. This reasonable is more pure, a more pure encoding in lambda calculus. As anticipated, effects in our language are basically just interrupt calls. How do we use them? Well, this is the syntax. It's very cumbersome, but fortunately that's how you do it. Because this is the number of the interrupt, so the code that tells what function you're calling. These are the values of the registers, so basically the parameters that you're passing to the interrupt. And then you have a continuation at the end. So basically we have effects. It's kind of continuation passing style. Yes. To see how cumbersome this is just a basic program that prints banana, and that's it. It's very verbose, but it's very cool. Now I'll leave you the word to talk about how.
Hi, this is myself from the future. Before continuing with the implementation, I'd like to show some actual code examples that we did not have the time to fit into the presentation. The first program I want to show you is one that computes the Fibonacci numbers. The way it does it is by using the Y combinator, which is a special function in the lambda calculus that has the property y of f equals f of y of f. Basically, this allows to encode recursion into the lambda calculus. The way it computes the Fibonacci numbers is by checking whether L0, which if we have a parallel with fib of x, would be x. It checks whether it is less than 2, and if it is, it returns 1. Otherwise, it applies the function itself, which is the parameter L1, to L0 minus 1, and it takes that and sums it to L1 applied to L0 minus 2, which is basically like doing fib of x minus 1 plus fib of x minus 2. Once we have all that, we apply it to 11 and we obtain the largest Fibonacci number we can compute in our language before running out of activation record memory. The second program I would like to show is one that prints the uppercase alphabet. It takes the letter A as a parameter and it checks whether the parameter is less than Z, which of course A is, and if it is, it prints it using an interrupt routine, and as a callback, it calls itself on L1 plus 1, which in this case is the parameter plus 1. So it's L1 and not L0, because the interrupt adds another layer of scoping, so we do need to increment all the indices. In fact, you will notice that if before the function itself was L1, now it is L2. At the end, after having printed the whole alphabet, it returns 0. This final example makes use of the return value of the interrupt calls, and what it does is very simple. It takes 2 key presses from the keyboard, and it returns the sum of the ASCII values of the characters corresponding to the keys that were pressed.
Well, we implemented it.
Yeah. All right. So, I have no idea how this goes, but I guess. Okay, so apart from the portion of memory in which we store the program itself, we have divided the rest of the memory into 3 stacks. One you're familiar with is the built-in stack, which is, for example, the one used by C programs. And the other 2 stacks are respectively the operand stack, which is what's used, for example, in the Java memory model for handling operators, and the activation record stack, which is used to hold information about a function call and handle dynamic and static links. Yeah, okay, so the first one is not as interesting as the other 2. So, to illustrate how the operand stack works, I will give an example of how we compile binary operations. So, if we have an operation, say, plus, okay, this is pseudo assembly code. We say we have E1 plus E2. So here will go the result of compiling E1. Here will go the result of compiling E2. And this code, what it does is it pushes on the operand stack the values of the results of the compilation of the computation, say. And then what we do is we pop the 2 values from the stack into 2 registers, and we compute the result of the operation and push it back on the stack. We don't actually use the primitive pop and push. We have made some macros, NASM macros, that basically handle the shifting and pushing of the various pointers. Okay, for the activation records, the things we care about are the caller's activation record pointer, which is used to return the control to the caller once we have called a function. The pointer to the current scope, which is the definition record pointer, which is used to go back and, for example, if we're inside a function and we want to access L1 or L0. So L0 is the parameter of the function. L1 is the parameter of the outside function. So we need to go back by one link in the chain and retrieve the correct parameter. So then we store the actual parameter. And if the actual parameter is a function, we also want to hold the definition record of the actual parameter. So in case we retrieve a parameter and it's a function and we want to call it, we must call it in its original scope. So we hold these 4 infos, basically. So compiling constants is easy. We just push the constant on the operand stack, and that's very simple to do. Compiling operations is also easy, and I won't repeat myself because I've already mentioned how it's done. Also because we're ludicrously late. Conditionals. Okay. For conditionals, we compile the guard, and then we perform a conditional jump based on whether the value that the compiled portion of the guard pushes is 1 or not. So if the result is 1, it jumps to the part of assembly code that encodes the then branch. Otherwise, it jumps to the negative branch, the else branch, which is done using labels and jumps that are written to the assembly code. Now, for how is it pronounced? Something of like that. The brain. For the brain indices, when we compile ln, as I said before, we want to go back the scoping link n times. So 0 times if it's the parameter, once if it's the outer function, and then n times in general. Okay. And so we have a pointer to the current activation record, and using an offset from the activation record pointer, we retrieve the earlier pointer, the pointer to the earlier activation record, and we do this a bunch of times until while decreasing a counter, and when the counter reaches 0, we return what we found. So yeah, this is done by calling a function called sequel after having moved the number n to ax. And I believe we have the function sequel here. So this is the function sequel, which moves to bx the current record and uses ax as a counter. And when the counter is 0, it jumps to endl. And endl, what it does is it does a bunch of things to retrieve the parameter. And if it's not, it continues, decreases the pointer, decreases the counter, changes bx to the pointer of the earlier scope record, and calls the loop. So, which we call loople because the function is called sequel, the loop is called loople, the end is called endl, and then we have the very endl, which we're very good at giving names to things. Okay, now for lambdas. So, when a lambda is compiled, we move this portion of code to a part of the compiled assembly code that is reserved to. It's basically the place where all functions go, and we give each function a fresh label to be able to call it uniquely, and the function contains the compilation of the body of the function, a bufferize command, which is a macro that what it basically does is it returns to the index space of the caller and does a bunch of things to preserve the values of the pointers, which are the activation record pointer, the operand stack pointer, and other pointers we use in the compilation. Another thing it does, of course, is it pushes the function itself. So a pointer to the function itself in memory, and a pointer to the current record, which is saved as its definition address, basically, as its definition scope. Compiling function application is very complex, and we have no time to explain it in detail. But when we make it public, there will be a link in the description, and yeah, you will see there's a markdown file in which we wrote for ourselves, in which we explained in detail. The general things is, so we have two different syntaxes, which is horrible, really. We have two different syntaxes for applying a function to a number, so this is first order application, and another syntax for applying a function to a function. This is not necessary because there are technical reasons why we could do a thing that allows us to remove the separation and the distinction, but it would make us use more space, and we have very little space, which will be a theme from now on. So, for example, one statistic that is significant is we can only print banana 5 times before we run out of space, of activation record space, because we do not have a garbage collection algorithm, which is very bad for now. So, given this, regardless of the distinction, the general scheme for compiling the application is we compile the first two before the function and then the argument, which may be a function. Now the function pointer, the function's definition record, and the argument, which may be a single integer or a pair, function pointer and activation record, are on the operand stack. We use these using what's for now a macro, but we may turn into a separate function to reduce the size of the code. We use these to create a new record, which is pushed upon the record stack and made the current record. Once this is done, the function obtained by compiling E1 is called in the scope defined by the new record. So, yeah, okay, it's a new function, it has a new scope, and we call it. And one thing I did not mention is that, of course, when we come back from the call, we want to restore all the things that we had pushed using bufferize. So there's a debufferize macro that does exactly this. You will see it on GitHub if you're interested. So, compiling tuples, we have mentioned how it's done. So conceptually, it's basically if L0 is 0, then return the first element of the tuple. If it's 1, return the first, the second. Well, okay, you start from 0, from 1, that's it. In practice, we generate a custom code that looks a bit more like how a switch is compiled, for example, on the Java virtual machine or even in C. Yeah, we have interrupt calls, which are compiled this way. So we first of all, we push the values of the input tuple on the operand stack. We pop them in a macro that sets the registers, fires the interrupt, and saves the result into a special part of memory, which keeps the result until we push the values we had saved in memory as the parameters of the continuation. The way this is done is by creating a new tuple containing the register values, which will then be passed as the parameter of the continuation, basically. And the surprising thing is that tuples are a static thing, and we need to create one at runtime. So the way we do it is a bit weird. So what we do is we keep a template of a tuple of length 8, so an 8 pole, something like that, and we do live coding basically. So we generate code at the end of the memory that is a copy of the template, but with the portions with the relevant portions changed to have the correct elements. So we have a new function which is pushed onto the pointer to which is pushed onto the operand stack, which is created runtime. It's very weird. It's a bit dirty, but we liked it. And yeah, okay. That's how we make tuples. Now for some live coding, but really we just run some of the examples that we made earlier. Do you want to do this? Do you? Oh, I should do it. Okay. Let me retrieve the. We have 3 minutes. This is going to be. No, we should do the. Okay. No live coding. We have. I will fetch the floppy disk. I've entered a floppy disk into the floppy disk thing. Okay. It's this one, isn't it? Yes. Okay. So I don't need this anymore. Okay, and it printed banana. Maybe on YouTube I will do. Okay. Maybe on YouTube I'll put some live coding part, but I highly doubt I will find the time to do so because I have to prepare an exam. So yeah, that was the seminar. Yeah, so the next step, of course, is to. Wasn't there? There was no other part of the. Okay. The presentation was over. The presentation was over.
Okay.
The presentation was over. So the next steps, of course, are to. With a nice zoom on my face. The next steps are to conquer the world using lambda calculus, because that's precisely what we're doing. Okay, thank you very much for coming. It's been an exhausting 4 hours, but I loved it, and I can't wait until September to start again. Okay.